This doesn't look right, so we're going to start back over. Now then, that looks better. Okay, so we're in section 4.1, and so we recapped just a little bit before I turned on the mic. So we talked about how to add two vectors, how to multiply a vector by a scalar, multiply a vector by a scalar, and add a vector. That's basically what we've talked about so far. So in the 4.1 blank note sheet, we've talked about page 1. And now we're to the example where it says if u equals 4, 0, negative 3, and v equals 1, negative 2, 6, find u plus v and v minus 2u. Okay, so I'm going to get you guys to go ahead and do that, and I'll catch up. And we might have done that one last time, or we may not have. Okay, so if I found u plus v, I'm just going to add their components. So that would be 5, negative 2, 3. So 4 plus 1, 0 plus negative 2, and negative 3 plus 6. Okay, my second one was v minus 2u. And as far as how you want to work it, you can even do it in your head. I don't, of course. But v is 1, negative 2, 6. Okay, and I almost got tricked by my own problem there for a second because I'm used to u coming first, and I was like, oh, it's v, and so I almost wrote u there. So be very careful. It said v first. Okay, so then it says minus 2u. So you can do this option where you say plus the opposite and multiply 2 times v, or you can say minus 2 times u, however you want to handle your sign. Okay, I personally prefer to handle the sign by leaving the negative there, and then I can multiply 2 through by u. So multiply 2 by this guy up here. So that's 8, 0, negative 6. Now how you choose to handle the sign is up to you. Now that I have those, I can say this is 1 minus 8, negative 2 minus 0, and 6 minus a negative 6 would be 6 plus 6. And that's how that one would look. Okay, so this was what we call 3-space. So this was ordered triples. And that's how those would look. Now then. You have a sheet. I just gave it to you earlier, that has the homework on the front page, section 141 through 45. And on the back page, it has what we say definition of vector space. It also has summary of important vector spaces. Now this definition of vector space, this is actually the one that comes from section 4.2 because it's a little better. But this also correlates to the R space in section 4.1. So if you have a vector space, which the definition, like I said, comes in 4.2, these properties hold. It has to be closed under addition. The commutative property holds, which means u plus v is v plus u. The associative property holds, which means if I add u and v and w, it doesn't matter if I add u and v first or if I add v and w first, I'm going to get the same answer. And that's what the associative property tells you. It says v has a 0 vector. V also has an additive inverse. And what you'll notice about those 5 axioms is that they all deal with addition. Okay, so then you have scalar multiplication, which is not like matrix multiplication, right? It's scalar, which means it's a constant multiplied through, or coefficient. So C, U is in V. Distributive property holds. You'll say there's 2 distributive properties. There are. Number 7 tells you that it's the distributive property in which you have 2 vectors. And number 8 is the distributive property in which you have 2 scalars. The associative property holds if you have the 2 scalars there, and there's also a scalar identity, which I call a multiplicative identity. Now, at some point, we'll talk about those. For your test and for your final, you don't have to memorize them, but usually I give you some kind of like little quiz type thing on write all 10 of them out, just as a random day in class, which I would, of course, tell you ahead of time. Now, the important vector spaces that I always do are R space, P space, which is polynomials, and matrices. Now, there are other ones there. You can see I scratched a few out, but those are the ones that I'm going to refer to for the rest of the section. Now, let's talk about that sheet for a second. I wish I had it uploaded into this document, but unfortunately I don't. One of the things it says on there is that V has a 0 vector, okay? Okay, so these are 3 random vector spaces. R2 is a set of all ordered pairs, R3 is a set of all ordered triples, and M22 is a set of all 2x2 matrices. So one of the questions I sometimes ask you is, what does a 0 vector look like for R5? Or what does a 0 vector look like for M22? Okay, so if I asked you a 0 vector question, and those are good short answer questions, the 0 vector for R2 would just be 0, 0, an ordered pair consisting of only zeros. Now what the 0 vector, I think it was axiom 4, what the 0 vector told you was that if I picked any element of R2, let's pick 1, 2, and I added it to the 0 vector, what I would get back is that element. So it's just like 0 in anything. If I add it to 0, I get that value back. Well, this would be the 0 vector for R2. And so that's what that little axiom was referring to. Okay, so I could ask you the 0 vector for R3. Well, this is how it would look. I could ask you the 0 vector for M22. That's how it would look. Okay, so those are really good short answer questions. I could also ask you an additive inverse. Now, unfortunately, asking you the additive inverse for R3 is something that's really hard to grade because there's so many possibilities, and you could argue your point. But if I was looking for something that's an additive inverse of R2, what I would probably say is negative x1, negative x2. Because for any x1 or x2, the inverse would be negative x1, negative x2. So you could say that was an additive inverse. Another thing my students have often said is this. That's an additive inverse. And technically they're right. It's an additive inverse of something, right? And so for every element in R2, R3, M22, M44, whatever it is, whatever vector space, for any element there is an additive inverse. Okay, so let's look at that 1, 2, negative 1, 2. If I had the value 1, negative 2, and I said find its additive inverse, this is what we're looking for. So if I put a negative 1 here and a 2 here, those would add together give me 0, 0. Okay? And so negative 1, 2 is an additive inverse for the value 1, negative 2. And this is what they mean by additive inverse. Now, so what will I accept for that answer? I would accept this. I would accept this. I would accept 1, 2. because that's also an additive inverse of something, right? So as long as you can explain your answer, I'll give you credit. But if I was talking about the generic additive inverse for this one, you could call it this. The generic additive inverse for this one, M22, you could call that. All right, let's see what else is in there. Okay, so I think that's it for that part. Now, on that little handout I gave you, you have a linear question to do. There are 2 more questions to do, but I want you to flip to the back really fast, the back of that packet. And on the back of that packet, we talked about closure in our last class. So I went back over the closure topics. So for example, if you look at that vector space axiom, closure under addition is number 1. So if I added 1, 2, and 3, 4, I got back 4, 6. So I added something that's an element of R2 to something that's an element R2, and what I got back was R2. If I added the matrix 1, 2, 3, 4 to 5, 6, 7, 8, so if I added a 2 by 2 matrix to a 2 by 2 matrix, I got a 2 by 2 matrix back. Scalar multiplication. If I took the number 4 and I multiplied it through 1, 2, what I get back is something that's still in R2. So that's what we talked about last time with closure. I also show you an example of something that's not closed. So if I gave you the set of ordered pairs in which x and y had to be odd, then I added 1, 3, odd, odd, to 5, 7, odd, odd, and when I added them, fix it, it's incorrect. What's 1 plus 5, you ask? What should 1 plus 5 be? 6. Okay, so fix the sheet. 1 plus 5 should be 6. But the point with that one is that I added an odd group to an odd group, but what I got back was an even group, and so that is why that one is not contained in the set. Okay, if you were watching this from my notes, it has an error in it that I need you to fix. Okay, and so this is on the back page of the 4.1 handout. When you add 1 plus 5, you get 6. And on the sheet it says 4, so fix that. But again, the point with this is I added something that had only odd entries to something that only had odd entries, and what I got back was something that had even entries. And so that's what we mean by not closed. All right, so that's the first part of that section 4.1, and then we have the last part. And so there are 2 examples left. This one's in 4 space. I'm not too bad about giving you 4 space, but I did here. All right, so we want to solve this vector equation out. Now, this is how this one is written, but you could also possibly see, you don't have to write this. Let me write this out for a second. In your textbook, you may also see a vector equation that looks like this one at the bottom. This one had words. It says, if U, V, and W solve for X, Okay, that's what it actually said. Okay, but in this particular case, x was already on a side by itself. But sometimes in your homework or in the textbook, it may give you a vector equation that looks like this at the bottom, and you're like, ooh, x is right there in the middle. So it may be that you have to physically solve and get x by itself first and then do your math. But really, there's no wrong way to do it. However you want to label it, you could make it work. But I think it's easier. If you have x that's not by itself, I think it's easier to solve it and put it by itself first. All right, so what I do know is that x is going to be a R4 vector. Okay, so x equals 3 times u. Okay, so I'm going to go ahead and take 3 times u. Okay, and you saw me add 5 and 1 earlier and get 4. So please double check. 12, negative 18, 0, 9. I like it. Now, as far as the other, you could distribute the negatives through v and w and then put those, or it's pretty easy to add them up in your head. V and w are here, so that's going to be a negative 1, 4, 13, 6. Yep. And now I'm going to perform this operation. So I'm going to get 13, negative 22, negative 13, and 3, I believe. And we'll double check it. 13, negative 22, negative 13, and I did not get the last one. Let's see what I did wrong. Oh. Negative 8. Oh. It's miscopied. Okay, so I've told you this since August, that if I'm going to miss it, I'm going to miss it because I miscopied it somewhere. Okay? So if you're looking at your sheet, this right here is a negative 7, and it just took that one little pinch for that part to be wrong. Okay, so now then, the u part's right. V plus w, this piece right here is no longer correct. Okay, all the rest of it's correct though. V, we're adding them, so it's negative 1, 4, 13. This is a negative 8. Okay. So the only thing that's wrong is that last little digit. So now I've got a 9 minus a negative 8. U, 3u. 9 minus a negative 8, which should be 17, I believe. But that's not on my sheet either. Good grief. 17. Okay, great. That is what it looks like. I'm happy with that one. So that's how it would work. Now, the point of this example is this. You don't know it yet, but this is a point. Later in this chapter, we're going to talk about something called a linear combination. And a linear combination means that you are able to write one vector as a linear combination of the others, which means pluses and minuses and scalars, and you're able to write them as a linear combination. It's also going to go back to questions of, I'm going to ask, is this a spanning set? And is this linearly independent? So if you can write something as a linear combination, it's called a spanning set. And I'm going to say, is this a spanning set, yes or no? And so remember, if you're finding it's a spanning set, or find if it has a solution that all ties into the determinant, and it's all going to come back all over again with the determinant, if the determinant is 0 or not 0, and so forth. So that is where this is leading to. Okay, on your next page, you have this problem And that is actually, I'm going to get you set up for the problem, but that's actually going to be your homework for this week. Because I didn't give you a full homework set, so I'm trying to give you a little bit of a break because I know you got a lot going on. So this is going to be your homework for the week. Now, after I get mine written down, I want somebody to double check it for me to make sure I didn't miscopy it.
Homework's just the back page?
Yep. Just this one little bitty problem. Well, I say little bitty, it's going to take the whole slide. Okay, so this is called writing as a linear combination. And to save me some time and to make you guys do some work and to give you an easy homework assignment, I'm going to get you to work this one out. Now, here's how it sets it up. First of all, we're looking for A and B and C, and your answer, I don't know the answer because I'm not going to look, but the answer is going to look something like this. Now, this is not the answer, but that's what a linear combination looks like, kind of like what you saw on the previous slide. That's what a linear combination looks like. So when you get this answer, this is what we're looking for. So my unknowns are going to be A and B and C. They're not going to be U and V and so forth. So here's how it's going to look. X is 1, negative 2, 5 equals A times 1, 1, 1 plus B times 1, 2, 3 plus C times 2, negative 1, 1. Okay, I'm going to double check my, my numbers. Great, thank you. You're very welcome. You got your phone, right? Okay, good deal. Okay. I have it worked out in my notebook somewhere. Just gonna make sure. Right, so here's how it's going to play out for you. You're going to set all of your element 1's equal. So 1 equals A plus B plus 2C. A times 1, B times 1, 2 times C. All your element in position 1. Okay, your second one is all your elements in position 2. Negative 2 equals A plus 2B minus 1C. And your third one would be 5 equals A plus 3B plus C. Now, I don't like my constants on the front, so I would rewrite it and say A plus B plus 2C equals 1. A plus 2B minus C equals negative 2. And A plus 3B plus C equals 5. And you're going to solve it. So it's back solving it like Gauss Jordan back from test 1, right? And so you're going to get your value. The other thing that you'll notice is I'm going to take my coefficients out. See those vectors? The vector that's behind A, that's your first column. 1, 1, 1 goes down. The vector that's behind B, 1, 2, 3, it goes down as a column. the vector that's behind C, 2, negative 1, 1, there it is, and then your constant vector would be 1, negative 2, 5 going down, okay? Now, later on, in the end of this section, you're going to set these up just like this, and I'm not going to say what's A and B and C. I'm going to say, does it have a solution? And if I ask you the question, does it have a solution, all you have to do is take the determinant of it. You don't have to solve it all the way out. All right, so this is your homework for Monday. Yep, today's Wednesday. Okay, so bring that, and that'll be your homework. If you have any questions, of course, you're welcome to message me, and I'll be glad to help you. All right, so that's your first packet that says section 4.1. You also have a packet. It's not a packet. It's a single page that says chapter 4 at the top. So it says an element in R4 looks like this. And this is just kind of a recap. If you had a random element in R4, it could look like this. Okay, and sometimes I'll ask you, give me anything in R4. Give me anything in M32. Okay? An element of M23 looks like this. It has 2 rows and 3 columns. Okay, and I just picked random numbers to put in there. So that's something that's in M23. Now we haven't talked about P space yet. So an element of P2 looks like this. Okay, so what's P? P in is the set of all polynomials of degree n or less. Now that or less ends up being a big deal later on, but it's a set of all polynomials of degree n or less. What's important about all of these groups, Rn, Mn, and Pn, is that they all behave the same way when applied under vector addition or scalar multiplication. So even though matrices and polynomials are not alike in any looking at them, they behave the same way when they're applied to those two operations. Okay, your vector space, going through this sheet again, your vector space definition is what I gave you that's on the back of your homework sheet. We've talked about singular matrix. A singular matrix is a matrix whose determinant is 0, and a singular matrix does not have an inverse. We also know the counterexample of those is also true. If the determinant is not 0, it's non-singular, and if the determinant is not 0, it has an inverse. And for us, having a unique solution is also important. You also have the definition of subspace there. That's actually section 4.3. It's written out really nicely. It's just given to you a little prematurely. But a subspace is closed under addition and closed under scalar multiplication, okay? And then it also has the 0 vector. So it says a subspace is a subset of V. So that means if it's a subset of V, that means it has to hold all of those vector space axioms, because V represents vector space there. So it has to hold all of those vector space axioms. And so, to be a subspace, it has to, that itty-bitty little part of it has to satisfy these 3 axioms. All right. Flip it to the back. On the back, we start with section 4.2. The very first thing in 4.2 is the definition of vector space, which I've given you earlier. So that's important. A vector space consists of 4 entities. Okay, so you had your vector space definition, first of all, and then you have this little fact A vector space consists of 4 entities. It has to have a group of vectors. Set is the word I'm looking for. Set of vectors, a set of scalars, and 2 operations. Okay. Now, we're going to jump over to an easy one where I'll show you where we're headed, and then we'll get out of here. The first ones aren't. The first ones are a little tougher, so let's go to the third one. It says prove that the set of all 2x2 matrices of this form is not a vector space. Okay, and so for this example, we go immediately from let's add and subtract vectors and do arithmetic operations that are really easy to do, and we go straight to theory. Okay, so this jumps into theory land. Now, in order, and you probably haven't done much theory at this point, but in order to prove that something is not a vector space, all you have to do is find one little thing that makes it fail, just one. I'm not going to ask you to prove that something is a vector space, because in order to prove that something is a vector space, you have to go through all 10 axioms, and it would take forever. I don't even do it in class. So I'm only on the test, I'm only going to ask you to do what's not a vector space. Now, it would help if I finished writing out the problem. Now, first of all, you have to know what this set looks like. A is a variable, which means it can be anything. B can be anything. C can be anything. But that bottom position, position 2, 2, has to be a 1. Okay, so if we're looking to see what it fails, it fails a whole host of stuff. There's lots of them that it fails. The first one that I would say that it fails is addition. So for example, this red matrix here is an element in that set. 1, 2, and 3 can be anything, but remember that last position has to be a 1. I can add it to this matrix. Okay, this blue matrix is also in the set, because remember the characteristic of this set is that position 2, 2 is a 1. So when I add these two matrices up using vector addition, I'm going to get 8, 16, 14, 2. Not a 1. Okay, now this doesn't satisfy, this doesn't answer the question. This doesn't prove it. Even though I know what you mean, you have to do a little bit more work. You have to answer it. Basically, you're also going to have to answer which axiom does it fail. Okay? So, tidying it all up, since there is not a 1 in the last position, it is not closed under addition. Now, that's all you had to say. You didn't have to write it out in full essay form either. But there's lots of things that it would fail. It would also fail the 0 vector. Because remember, the 0 vector would have to be 0, 0, 0, 0. and that doesn't have there, so it fails that one. It fails scalar multiplication. Let's say you multiplied a 2 through any of those vectors, then you would have a 2 in that position. Okay, so it fails scalar multiplication. It fails additive inverse, because there would be nothing that I can add to a 1 that would cancel it out. There would be a 1 there, because 1 plus 1 would be 2, right? So there's no way to get a 0 using the additive inverse. It would also fail that one. Not sure about the rest of them off the top of my head, but I know that those it easily fails. And remember, if you're proving something is not a vector space, you just have to show 1. That's it. Okay, so that's where we'll pick up next time. We'll go through that little sheet, that 4.2 sheet, and we'll talk about proving that something is not a vector space. And then we'll continue with that on Monday and prove that something is a subspace. So those kind of go together.